Okay, I like this one. So we're going to make time flow independently of the user actions. Up to this point, our game has been turn-based. So you have to wait for the user to type something, and then, if they typed look, then all the creatures have a chance to move, and then you wait again. And if they type, if the user goes to another room, then the creatures will move again. So what we're going to do instead is we're going to give the game world its own separate execution thread, so that means that all the entities are moving independently on a time schedule, and the user, if the user goes off to lunch, the whole world could have changed. So before we can do that, we have to talk about threading. So threading is a process which I can only assume is a magical one by which thread is used to remove eyebrow hairs, if I understand this correctly. That's not the kind of threading we're going to do. We're going to be creating independent execution processes, which can be spawned to run parts of your program independently. They don't actually run in parallel unless you have multiple cores and you have it set up correctly. But even a single CPU can simulate multiple things running simultaneously by rapidly switching between the program's individual commands as they're running. So let's sort of do a few short tests and figure out how this works. The magic that makes this all possible is something built into Java called a runnable interface. So a thread, the name thread, refers to an independent execution process. And you can create a thread. You can instantiate thread by giving it a class that implements the runnable interface. And you'll see what this looks like in just a second. The runnable interface consists of just a single method called run. And this run method contains whatever code you want to run independently. So here's an example. My threaded class, we've got a constructor. Every single time we construct the threaded class, we construct it with a new ID, so that way we can tell which objects are running which things. And all it does is it loops from 0 up to a fixed maximum value, and it prints its own ID and then what step of the loop it's on. Okay, so you could run code that looks like this. Actually, here, let me jump to IntelliJ. Okay, so here's the same code in IntelliJ. This is my threaded class. Here I am instantiating my threaded class with some different IDs, A, B, C, D, and now we have 4 different objects. And then I can run the run method on each of the objects. So this is not threading yet. And you'll see, well, hopefully you'll see. Let me run it. Okay, so it's going pretty quick here. Oh, it's running the wrong thing. It's running the threaded version. Okay. So you see all the A's display, then all the B's display, then all the C's display, then all the D's display. My output buffer isn't that big, but that's what we would expect under ordinary conditions. Object 1's run method has to complete entirely before we start Object 2's run method. So that is not yet threading. We're not running independently. So here's the version where we're running independently. In this case, we have 4 different thread objects, and you see that we're instantiating thread, and the constructor argument is an instance of a runnable class. So I couldn't give it an object here that didn't implement the runnable interface. But what thread is doing is thread is now sort of a wrapper around this object. And then when I tell thread 1 to start, what it does is the thread handles running my class's run method all by itself. And you'll see what's going to happen now is when I run the program, you'll see all 4 of these displaying their outputs intermixed because they're all running simultaneously. And actually, let me display, I'm going to display some stars here at the end. And you should see this row of stars go by pretty quick, I think, because it'll happen like right at the very beginning. So there it was right at the very beginning, and now you can see a mix of A's and C's and D's. So here you see A is running a bunch of loops, and C is running a bunch of loops. So this is the multiple execution processes running in simulated parallel. And what we had in ours was something like this. We had a thread variable, and we instantiate thread, and we give it our runnable class, and then we tell the thread to start. You don't even really need to assign the thread to its own variable. Instead, you can wrap it in parentheses. You can say, make me a new thread, and as an input to the thread, we'll construct a new runnable class. But then we never assign thread to a variable. Instead, we just wrap it in parentheses and tell it to start. So this sort of one-liner is the usual thing that you see. All right, so how are you going to apply this to your game? You're going to have your level, or in yours it might be called graph, implement the runnable interface. And what do we want our whole game world to do independently? We want it to be in an infinite loop where it updates all the creatures and then it sleeps for a certain amount of time. So that's what we're going to put in our run loop. It's this while true, which loops infinitely, and you run your own update all creatures method, and then thread.sleep, you can give it a constant that you define, which is how much time it should sleep in milliseconds. I think you should set this for something like 5 seconds or 10 seconds, but you have to do it in milliseconds, so like 5,000 or 10,000. Then inside your main, you actually have to create a new thread with your game world and tell it to start. So here's my main method inside my main class. I've hidden all the initializations where I create the level and I create the player and all that stuff. But then once all those things are created, then you create a new thread for your level and you tell it to start. And then you can have the user game loop happening down here.